Hello. I previously recorded this talk just with my face. I didn't realize that I could actually share my screen so you could actually see my images. So I've actually discovered I can do that. So I'm going to give this talk now on Zoom. And so here goes. It's a talk about my book, The Magicians. Now, Antarctica was discovered by people who went out in ships and discovered it. But Neptune was discovered by a man sitting at a desk in Paris with a quill pen. And this, I think, illustrates the central magic of science, that it's possible to write down an equation, a mathematical formula on a piece of paper, on a whiteboard, on a blackboard, and it predicts the existence of something previously unsuspected, that when people actually go and look for it, they find really exists in the outside universe. Now, this magic is so magical, so miraculous, that even the scientists can scarcely believe it's possible. So famously, Einstein did not believe two predictions of his own theory of gravity, black holes, and the Big Bang. So what I'm going to do in this talk is I'm going to give you some examples of the scientists who demonstrated the central magic of science, the magicians I call them, and at the end speculate on why this magic works. But first of all, I want to just explain what science is and what science does. 3.6 million years ago, three of our ancestors walked across a bed of freshly fallen volcanic dust, and they left their footprints there. And those footprints can be seen today at Laetoli in Tanzania, and they're intensely evocative. You look at these footprints and you think, who were these three individuals? How were they related to each other? And what was their mission that day, tens of thousands of centuries before the birth of civilization? Now, of course, we'll never know the answer to any of those questions. However, there are some things about the thought processes of these people that we can imagine. So, just like us, they lived in an unpredictable and chaotic world. But there were certain things that were predictable. So, for instance, the sun came up once a day. The moon went through its phases every 28 days. The seasons rolled on year after year. But although these people, our ancestors, would have noticed these patterns, these regularities, they probably didn't speculate much more. Everything changed because of this invention in 3000 BC, the invention of writing. And once you could write, you could record things that you saw in the heavens. And if you assembled those recordings over months or years or even decades, you could discern much more subtle patterns in the heavens. And this gave the people who could do this the ability to predict spectacular celestial events, such as total eclipses of the sun, when the moon, the disk of the moon moves across the sun, blots it out, and the earth is plunged into darkness at midday. And the priests and the kings and the emperors they worked for gained tremendous power over their populace by being able to make these predictions. But that power was nothing compared with the power of science, which arose in the 17th century. Because what science did was it found the it found the laws which underpinned the patterns. And those laws were, first of all, portable. So, for instance, Isaac Newton was able to determine the law of gravity from the motion of planets, and in particular, the motion of the moon. But once he got that law of gravity, he could use it in an entirely different domain. And Newton used it to show why there were two tides in the ocean every 25 hours. But in addition to being portable, these laws were mathematical. They could be written down as a mathematical formula on a piece of paper. Okay, so that's science and what science does. So what I'm going to do now is give you the first of my magicians. His name was Urbain Le Verrier. He was a French astronomer in the middle of the 19th century, and he was interested in this planet. The planet is Uranus, or Uranus, however you like to pronounce it, and it was discovered in 1781 by this man, William Herschel. Now, William Herschel was a freelance musician who grew up in Hanover in Germany, but in the late 18th century, he moved from Hanover to Bath in the West Country of England. He came with his sister, Caroline, who incidentally discovered more comets than any other woman in history, except for another Caroline who lives today, Caroline Shoemaker. Well, Herschel got himself a job as an organist in Bath, but his real passion was not music, it was actually astronomy. And he built in his garden in Bath some of the biggest telescopes, most powerful telescopes of his day. And it was with one of those telescopes on a winter's night in 1781 that Herschel saw a tiny fuzzy disk in the viewfinder of his telescope. Now, at first he thought it was a comet, but as he observed it over the following days, he realized that it wasn't following the orbit of a comet, it was following the orbit of a planet. He discovered a new planet. Now, this planet, Uranus, was a sensation because it was the first planet unknown to the ancients. So unknown to the Babylonians, the Greeks, the Egyptians. And it was the first planet discovered in the age of the telescope. Incidentally, Herschel wanted to call it George because he was an immigrant from Germany and he wanted to be accepted in his adopted country. But imagine if he got his way, going out from the Earth, we would now have Earth, Mars, Jupiter, Saturn, and George. But Uranus was the name that stuck. Now, immediately he discovered this planet, which I should say doubled the size of the solar system overnight. It was twice as far away as Saturn, the previously known most distant planet from the sun. As soon as you discovered it, it was realized that it had been seen before. In fact, it had been seen about 100 years before by John Flamsteed, who was a contemporary of Newton's. And Flamsteed had not actually realized it was a planet. But the point is that immediately there were positions of this planet in the sky available spanning about a century. So it was possible to deduce its orbit. But this produced a problem because whenever its orbit was calculated, and that orbit would predict where the planet would be maybe in a month or 6 months' time, when people went to look, it was never where it was predicted to be. It always wandered from its predicted orbit. So this was a huge puzzle. So this is where Urbain Le Verrier comes in, because he guessed that there was yet another planet even further from the sun than Uranus, and that its gravity was tugging on Uranus and perturbing its orbit. And he set out to find out where that planet would be in the sky. Now, this was a horrendously difficult problem to solve. You see, the problem is that Newton's law of gravity is a universal law of gravity. And that means that every chunk of matter tugs on every other chunk of matter with gravity. So Uranus was not only being tugged by the gravity of this unknown planet, it was being tugged by the gravity of the Sun, the Earth, Venus, the two giant planets, Jupiter and Saturn, all the planets in the solar system. So the problem, the horrendous mathematical problem that Le Verrier faced, was to subtract the effect of all these other planets on Uranus and be left with the effect of the unknown planet. Anyway, he managed to carry out these calculations. I mean, a tremendous feat because I mean, any error would have destroyed them. And he discovered that the hypothetical new planet should be seen between the constellation of Capricorn, the goat, and Aquarius, the water carrier. So once he knew this, he went to the director of the observatory in Paris. He was at the Paris Observatory, and the director's name was Francois Arago. And he said to Arago, "Can we look for this new planet?" And Arago said, "No." But this wasn't really unreasonable. You see, national observatories like the one in Greenwich and the one in Paris had been set up principally to record the positions of stars for navigational purposes. And a lot of people were involved in this quite hard and concentrated work. And Arago didn't want to, spare anyone for this search. And the second reason that he was reluctant to look for this planet was that nobody in the history of the world had ever predicted the location of a new planet. It was just too ridiculous for words. So Leverrier became very frustrated, but eventually he had an idea. He realized that what he needed to do was contact an astronomer, a lowly astronomer, one who wanted to make their name, because they might be willing to take a look. And he remembered that a year before he'd had a letter from a man called Johann Gaul at the Berlin Observatory. And Gaul had sent Leverrier his thesis. And Leverrier was quite an arrogant man. He hadn't even bothered to look at it. But suddenly he picked up the thesis and started writing a letter to Johann Gaul, in which he said, "What a wonderful thesis you've produced. Sorry for the delay. Would you mind looking for this new planet?" And Gaul received this letter. He was not a vindictive man. He forgave Leverrier for the delay, and he was intrigued, and he thought he would like to look for this planet. So he went to the director of the Berlin Observatory, a man called Joseph Encke, and he said, "Can we look for this planet?" Well, Encke was as reluctant to look for the planet as his counterpart Arago in Paris. However, it turned out it was Encke's 55th birthday, and that night he was going to have a birthday party. So he would not be using the giant refracting telescope, the Fraunhofer refracting telescope at the Berlin Observatory. So by a piece of luck, Gaul was able to use this telescope, and he roped in an astronomy student at the observatory called Heinrich d'Arrest, and at midnight on the 23rd of September 1847, the two of them started searching for Leverrier's hypothetical planet. And incredibly, within 1 hour, they had found something. A tiny little fuzzy ball appeared in the viewfinder of the telescope, and it was not on any star map. What's more, it appeared as a tiny ball. Now, stars are so far away that even in the biggest telescopes, they're pinpricks of light. Planets appear as tiny little disks. So they'd actually discovered Leverrier's planet. And of course, it would be named Neptune. And it was a sensation of a completely different order to the discovery of Uranus by Herschel. You see, Herschel had discovered his planet by accident, but Gaul had discovered his planet because it had been predicted by a man sitting at a desk in Paris with a quill pen. This had never happened in the history of science. It demonstrated the tremendous power of science, that you could actually discover things from a desktop. But even more, it showed the power of Newton's law of gravity, because it could predict, or it could explain, not only what we could see, the motion of the planets and the moon, but it could actually predict the existence of things that we couldn't see. Now, it turned out that Leverrier became a scientific superstar, and he traveled around Europe, and he was courted by kings and queens, and he loved that feeling, and he wanted to have that feeling again. So he had found an anomaly in the outer solar system. Next, he turned his attention to the inner solar system. Was there a planet that was moving in a way that could not be explained? And incredibly, there was. The nearest planet to the sun, Mercury, wasn't moving as was expected. So Leverrier proposed that there was another planet even closer to the sun than Mercury. He called it Vulcan, and he postulated that it was Vulcan's gravitational tug on Mercury which was perturbing its orbit. Well, for 50 years afterwards, people looked for Vulcan, and some people saw it and some people didn't see it. But it turned out it was an illusion. Incredibly, there was a different reason for the perturbation of the outermost planet Uranus to the perturbation of the innermost planet Mercury. In the first case, it was the existence of an unknown planet. But in the case of Mercury, it turned out, incredibly, that Newton's law of gravity was wrong. And in 1915, Albert Einstein came up with a better law of gravity, which we call general relativity, and it predicted perfectly the motion of Mercury. But Vulcan survives as the birth world of Mr. Spock from the TV series Star Trek. My next magician is this man. He's James Clerk Maxwell, a Scot, and this is his statue in Edinburgh. It's in Edinburgh because Maxwell went to school in Edinburgh. At school, amazingly, he had the nickname of Dafty. And this is quite amazing because he would turn out to be the most important physicist between the time of Newton and Einstein. So what an incredible irony. Why was he called Dafty? Well, his mother had died when he was 8 years old. She died of stomach cancer at the age of 48, the very same age that Maxwell would die of the same cancer. And so he'd been brought up by his father at Glenlair, which was near Dumfries, which was the family estate. And his father had not been very good at dressing him. He dressed him in country clothes. So when he came to sophisticated Edinburgh to go to school, and he was dressed in these bucolic clothes, that was why his schoolmates made fun of him. Anyway, he finished school at Edinburgh. He went to Cambridge University. And when he finished at Cambridge University, he was very interested in electricity and magnetism. And these were the kind of buzz subjects, the really exciting frontier of physics at that time. In the late 19th century, or late 18th century, Luigi Galvani in Italy had shown that electricity could animate dead things. It could make the leg of a dead frog twitch. And this has obviously captured the imagination of an 18-year-old Mary Shelley, who had written Frankenstein, in which electricity animates a dead person to create Frankenstein's monster. So when Maxwell left Cambridge, and when he was, he had this interest in electricity, it was considered by many people to be satanic, but a complete mystery. So he wrote to William Thomson, who would later be Lord Kelvin. Thomson was involved in the laying of the first telegraph cable across the Atlantic from England to America. And he asked Thomson what he should read to get up to speed on what was known about electricity. And Thomson told him to read the works of this man. This man is Michael Faraday. Now, Michael Faraday had had as different an upbringing as it was possible to imagine from Maxwell's. Whereas Maxwell had grown up on a country estate owned by his family, Faraday was the son of a poor blacksmith in Marylebone in central London. And at age 14, he'd been apprenticed to a bookbinder in Marylebone. But that bookbinder had encouraged Faraday to read the books that he was binding, and many of those books were scientific. So Faraday educated himself in science. And he would have continued working at the bookbinders forever, but for a chance event. One day, a man walked into the bookbinders with a spare ticket for the talks of Humphrey Davy. Now, Humphrey Davy was the most famous scientist of his day. He discovered many chemical elements. He was so famous and so revered that he was even given an honour by Napoleon when Britain was at war with France. And he gave these lectures at the Royal Institution just off Piccadilly in London. And they were huge events. And he was so flamboyant that women would actually faint in his lectures. Well, anyway, the man couldn't go to these lectures, and he gave his spare ticket to Faraday's boss. And Faraday's boss gave the ticket to Faraday. And this ticket would turn out to be like the golden ticket in Charlie and the Chocolate Factory, because it would eventually change Faraday's life. He went to Davy's lectures. He was incredibly impressed, and he made fantastically detailed and beautifully illustrated notes of the lectures, which he later sent to Davy. And Davy was incredibly impressed, wanted to give Faraday a job, but he had no vacancies. And it was actually a long time later, many months later, that to Faraday's surprise, a carriage drew up outside the bookbinders. A man got out with a letter from Davy. Davy said that his bottle washer had been caught fighting, he'd fired him, and the job was Faraday's if he wanted it. So Faraday became Davy's assistant. Eventually it would become clear that even though Davy was a great scientist, his greatest discovery would turn out to be Michael Faraday. So they worked together on electricity, but eventually Davy died and Faraday became his successor as president of the Royal Institution. Now, before Davy died, a Danish physicist had discovered a connection between electricity and magnetism. It turned out that if you put an electric current through a wire and then you moved a compass needle around it, the compass needle kind of moved in a circular direction, as if there was a kind of a whirlpool of force, a circular force going around the wire. So there was this unexpected connection between electricity and magnetism. And Faraday, as he thought about electricity and magnetism, began to try and visualize what it was like. So if he held two magnets together, it was clear that they forced each other apart. There was something in the space between the magnets. And he imagined a magnetic field, a magnetic force field that extended from a magnet and pulled or repelled anything that came within that field. And he imagined all of space filled with magnetic and electric fields. The magnetic fields like kind of vortices, like tornadoes, the tornado of magnetic force around a current carrying wire. So this idea he tried to publicize of a magnetic field, and he was humiliated by the scientists of the day, the educated physicists, the Oxford and Cambridge educated physicists, because Faraday had no mathematical background, no conventional education. He was self-educated, but he had this visual picture. But this visual picture ended up in him doing experiments that no one else would do. So he used the tornado of magnetism that he could imagine around a current carrying wire to create the world's first electric motor. And so it was an incredible sight, an electric motor whirring in Faraday's laboratory, which was in the basement of the Royal Institution. So what an incredible sight that must have been, with horse-drawn carts clattering past on the cobbles outside, a kind of piece of the 20th century that had fallen through some kind of crack in space-time into the 19th century. But no one would accept his ideas, and again he was humiliated for having them. But then one day Faraday got a letter from James Clerk Maxwell, a man he didn't know, but a Cambridge educated physicist. And Maxwell said he believed in Faraday's idea of the magnetic field. And you can just imagine that Faraday, who was 40 years the senior of Maxwell, would probably have been almost in tears. He was a very emotional man to suddenly find that there was one of the greatest physicists of the 19th century actually believing him. So Maxwell's job was to turn Faraday's visual picture of electric and magnetic fields that filled all of space, to turn that picture into something mathematical that everyone else would understand. So what physicists would often do was they would create models of the phenomenon they were trying to explain. So mechanical models using analogues from the everyday world. And what Maxwell did was he imagined that all of empty space was filled with, so here's the picture, sorry, of the magnetic field around a magnet. And Maxwell imagined that all of empty space was filled with tiny invisible cogs, toothed cogs. So a magnet would turn a cog which was in contact with it, and that cog would turn another cog and another cog, and by this means the magnetic force would be transferred across space to a piece of metal or another magnet. And in this way, Maxwell was able to explain the fundamental feature of magnetic fields, that they were circular, that they circulated around something like a current carrying wire or even a magnet. And in order to fit more and more of Faraday's observations, Maxwell had to modify his model. So he made his cogs move more easily in a material like metal, because it was known that magnetic fields or magnetic forces were concentrated inside metals like iron. He made these cogs springy, and he added more and more tweaks to his model. But eventually he kind of gave up in despair and threw away the whole model. And he realized that there was no description of magnetic and electric fields in terms of everyday objects. So he was the first physicist in history to realize that the fundamental reality that underpins our world has no analog in the everyday world. And so he realized that the electric and magnetic fields could only be described mathematically. And he described them in terms of these equations, these mathematical formulae that we now call Maxwell's equations. They are so famous that physics students put them on their t-shirts. All you need to know is that D and E are electric fields and H and B are magnetic fields. And in fact, these equations, which we call Maxwell's equations, were not due to Maxwell. Maxwell wrote down 20 equations describing the electric and magnetic fields. But it was a man called Oliver Heaviside who reduced them down to the compact set of 4 we know and love today. Well, Maxwell realized when he wrote these equations down that it was easy to manipulate them to create what we know now as a wave equation. And a wave equation shows that a wave is permitted. In this case, a wave through the electric and magnetic fields, but a wave exactly like a wave on, or ripples on the surface of a pond. And Maxwell's equations gave the speed of a wave of electricity and magnetism, a wave rippling through the magnetic and electric fields that permeated empty space. And they gave that speed in terms of 2 numbers. And Maxwell, at the time he made this discovery, was at Glenlair on his summer holidays with his wife Catherine. At the time, he was a professor of physics at King's College in London. And he knew the two numbers he needed had been measured by German physicists and were in a textbook in the library at King's College. So he couldn't really get any further with his theory, but at the end of the summer, he came down on a train from Scotland to London with his wife Catherine. They brought her pony Charlie with them because they used to ride their horses in Hyde Park in London. And he went back to King's College. So they lived in a house just behind Kensington Palace. He would take the horse-drawn omnibus, the 4.5 miles, to King's College in the Strand. And when he did so, he rushed into the building, he rushed to the library, he found the textbook, he found the two numbers he needed, he plugged them into his theory, and he discovered that the speed of an electromagnetic wave was the speed of light. So he was the first person in history to realize what light was. Light is a ripple through the electric and magnetic fields that permeate empty space. And if that ripple is vibrating or oscillating quickly, then we see it as violet light. And if it's oscillating slowly, we see it as red light. So the colors of the rainbow are simply different vibration speeds of the electromagnetic wave. But as he left King's College that day, knowing that light was an electromagnetic wave, the only person in the world who knew that, the only person in history who knew that, and he came out onto the busy Strand with its horse-drawn carts and its costermongers and its beggars, the bustle of Victorian London, he realised something else, and that was that his theory posed no restriction on how fast or how slow an electromagnetic wave could oscillate. What this told him was that it was possible for the existence of waves that oscillated more quickly than violet light or more sluggishly than red light. So beyond the edge of the spectrum, which is conventionally shown with 7 colours, were millions, literally millions of invisible colours that nobody had suspected. So his mathematical equation he'd written down on a piece of paper had predicted the existence of what we now call the electromagnetic spectrum, a vast array of invisible waves which are passing through the air all around us. Now, Maxwell didn't get the chance to prove that this was correct because, as I said, he died at age 48 of stomach cancer. So we have to fast forward a decade and a half to 1888 and Karlsruhe in Germany. And this man, Heinrich Hertz, who was a 37-year-old, and he did this experiment. Now, what's on this tabletop, on his laboratory tabletop, may look a bit complicated, but basically on the right, he has a high voltage source which generates an electric current which stutters backwards and forwards across a tiny gap. So it creates a spark in a tiny gap in the electrical circuit, which stutters backwards and forwards. In today's parlance, we would call that a transmitter. And to the left is a loop of wire with a gap in it. And today we would call that a receiver. And when Hertz generated a stuttering spark in the transmitter on the right, he noticed that there was an answering spark in the receiver on the left. Something invisible had traveled through the air for 1.5 meters and created that spark. And he knew immediately what it was. It was Maxwell's invisible electromagnetic waves. And today, of course, we would call those waves radio waves. When asked what was the use of these radio waves, Hertz said, no use whatsoever, which is incredible, really, because Hertz effectively created the ultra-connected world of the 20th and 21st century, where invisible electromagnetic waves of just crisscrossing the air wherever we are, taking voices and computer communication across the world. So all of this was the prediction of a mathematical formula written down by James Clerk Maxwell. My next magician is this man. His name is Paul Dirac. He was a British physicist. He was one of the architects of quantum theory, the theory of the microscopic world of atoms and their constituents. He was one of the only English contributor in the mid-1920s. And he was a very strange man, as this biography tells us. He was at Cambridge University. He would work very, very hard for 6 days, and then he would take Sunday off and he would hike around the villages on the outskirts of Cambridge, and he would climb trees in his suit and tie. And when a student put up their hand in one of his lectures and said, "I don't understand, Professor Dirac," he would say, "That's a comment, not a question," and continue his lecture. He had a friend called Peter Kapitsa who would win the Nobel Prize, as would Dirac. Kapitsa was a Russian, and he was always getting Dirac to, well, always trying to get Dirac to read Russian literature. And one Friday, he succeeded in getting Dirac to take home Crime and Punishment. On Monday, when Dirac came into the lab, Kapitsa was very, very keen to know what Dirac thought of it. And all Dirac said was, on page 357, the author has the sun rising twice in one day. That's it. So really, Dirac was the kind of Mr. Spock of physics. I mean, today we would probably say that he has a good chance of being on the autistic spectrum. But whereas he was socially inept, he was a wizard at quantum theory. And in the late 1920s, we're talking about here 1927, the problem was to unite quantum theory and Einstein's theory of gravity. So the two towering achievements of early 20th century physics. So quantum theory was a theory of the atom and its constituents, and relativity was a theory about what the world looked like if you traveled close to the speed of light, which is a speed about 1 million times faster than a jet plane. So way beyond normal experience. So the problem was this: if we take an atom, the electrons are whirled around because there is an electric force between negatively charged electrons and protons in their nucleus at the center. So that attraction is what whirls an electron around, just like a planet is whirled around the sun by gravity. Now, if we think of hydrogen, which is the simplest atom, hydrogen has a single proton, positively charged in its nucleus, and a single electron. And that electron travels around the nucleus at about 1% the speed of light. So you don't need relativity. But as you add more and more protons to the nucleus to get heavier and heavier atoms, the electric force gets stronger and stronger, and the electrons get whirled around faster and faster, until eventually, when you've got an atom, say gold, the electrons are being whirled around at nearly the speed of light. So you actually do need to unite quantum theory with relativity, or to figure out, to understand an atom. Okay, you have to make quantum theory compatible with relativity. Now, nobody knew how to do this. It was a really serious problem, mainly because quantum theory is a theory of chance. We can never predict exactly what an electron will do. We can only predict the probability that it would do something. Whereas relativity is a theory of certainty. We actually know what the world will look like when we're moving near the speed of light with complete certainty. So uniting these two things is very, very hard. And it turned out that Dirac was not like other physicists. Maxwell was pretty much like you and me. He looked for everyday analogues to try and understand things. I mean, obviously he was a genius, but basically he used thought processes that we can all understand. But Dirac did not. He actually was, what he loved was pretty mathematics. And what he liked to do was fiddle with, on a piece of paper with pieces of mathematics to find something that would hopefully describe the outside world. So he was not motivated by models of the world like Maxwell or anyone else. And in November 1927, sitting at his desk in his Spartan office in St. John's College, Cambridge, he plucked effectively from thin air an equation, a formula that described a relativistic electron, an electron traveling near the speed of light. And this was really quite incredible. He was able to show immediately that it explained something about electrons that no one understood, which was that they have spin, they behave like tiny spinning tops. So his theory turned out, or his equation turned out to be amazingly successful. However, to his dismay, he realized that the machinery of his equation was duplicated. So it not only described a negatively charged particle, an electron, it also described a positively charged particle with the same mass as an electron. Well, this seemed ridiculous to Dirac. At the time, only 3 subatomic particles were known: the electron, the proton, and the photon, the particle of light. Who wanted a 4th one? So Dirac did publish his Dirac equation, and it was generally dismissed by other physicists, even the great physicists of the day. They thought that maybe it predicted something about an electron by accident, because really, who could believe in there being a positively charged electron? The Dirac equation is one of only 2 equations inscribed on flagstones on the floor of Westminster Abbey. The other is an equation by Stephen Hawking, which predicts the temperature of a black hole. So Dirac predicts the existence of this positively charged electron, but no one believes in it. So the story moves 6,000 miles away to California. And this is Caltech, the California Institute of Technology, which is in Pasadena. We would call it a suburb of Los Angeles, really, although it's deemed a separate city. It's actually part of Los Angeles, the conglomeration of Los Angeles. This man here is Carl Anderson, and he was interested in these cosmic rays. They had been discovered in 1912 by an Austrian physicist called Victor Hess. And Victor Hess had discovered them by putting a particle detector experiment in a balloon, and he discovered that as the balloon rose higher and higher into the air, he got more and more particles, which implied that there was a source of high energy particles out in space, and they were dubbed cosmic rays. Now at Caltech, Anderson's supervisor, Robert Andrews Millikan, who actually got a Nobel Prize for measuring the charge on an electron, got very interested in cosmic rays. And he thought that they were probably very high energy light, what we call gamma rays. And he set Anderson the job of actually finding out something about them. Now, gamma rays would be very difficult to detect, but the idea was that as they came down through the atmosphere from space, they would occasionally hit an electron in an atom and kick it, and you might be able to detect the electron. So within this apparatus is a kind of a transparent glass box the size of a biscuit tin, which contains moisture. I won't go into the details of how it works, but basically, incredibly, if a charged particle like an electron flies through such a box, it's called a cloud chamber, it leaves behind a trail of tiny beads of water, tiny little water droplets. And if you illuminate that trail with a flashlight, you can photograph the trail of a subatomic particle, even though it's millions of times smaller than anything that could be seen with the naked eye. So within this apparatus is a cloud chamber. And really, to learn anything about such a particle, you need to bend it with a magnetic field. So a very, very fast particle will spend very little time in the cloud chamber, and therefore will be bent very little, have a straight path. A particle with not much energy, will spend a long time traversing the cloud chamber and will be bent a lot. So what you want to do is create a magnetic field, the strongest magnetic field you can. And Anderson had done that by actually wrapping a coil of wire, what we call a solenoid, around this cloud chamber. And he put the biggest electric current through it that's imaginable, or that he could, or that was available to him. And of course, everybody knows that when you put a big current through anything, you get lots of heat. So he had to cool this apparatus. And what you're actually seeing, this coil is not his solenoid, it's the coil of metal tubing around his solenoid. And he pumped water about 40 gallons a minute through this solenoid. It would come in at room temperature and come out at boiling point. That's how hot the electric current going through his solenoid was. And he would pump this water out. He was on the 3rd floor of the aeronautics building, the Guggenheim building at Caltech, and it would go down a pipe, down the wall, down an alleyway, out across California Boulevard to a residential street called Arden Road. And as you can imagine, the residents were completely horrified because at midnight, walking their dogs, they would see steam billowing from the drains in Arden Road. And it took a lot of sweet talking by Anderson's supervisor, Millikan, to calm them down and allow this experiment to go ahead. So to cut a long story short, in August 1932, Anderson obtained this picture. Don't worry about the big black streak across the middle of this picture. That's a lead plate which was inserted in the cloud chamber. The important thing is the trail which goes from top to bottom. And this bends in the opposite direction to an electron. And really, when Anderson determined everything he could about this particle, he realized that it had the mass of an electron, but an opposite electric charge. It was a positive electron. Anyway, it really puzzled him. He couldn't understand why he obtained this picture, but he was an experimentalist, so he had to believe it. So he wrote a paper, he sent it to a journal in Washington, declaring the discovery of this particle. And it so concerned him that just before it was going to be published, he even phoned the offices of the journal and said, please pull the paper. I'm too worried about it. But they said, it's too late. We've already printed the journal. So it came out. And nobody took any notice because, again, it didn't fit into what people expected. But eventually, it was realized that he had found Dirac's particle, a positive electron, what we now call a positron. And it turns out really that the Dirac equation is probably the most productive equation with the most consequences of any equation ever written down by any physicist, because what it did was it predicted the existence of a completely unsuspected universe of antimatter, because it wasn't simply that there existed a positive version of the electron. Every single particle had an antiparticle. So the proton had an antiproton. The neutron, which was actually discovered in 1932, the same year as the positron, that had an antiparticle, an antineutron. So there was a completely unsuspected universe of antimatter. Now, of course, we live in a universe which is predominantly matter. And one of the biggest mysteries in physics is why that's so. Because every particle process we know of produces an equal quantity of matter and antimatter. But because antimatter and matter annihilate when they meet, antimatter doesn't actually get very far because it's in a universe of predominantly matter. And you may think that antimatter is the stuff of science fiction, but in fact it has many very mundane uses. For instance, in PET scans, which a PET scan is a positron emission tomography scan. And what doctors do is they inject into a patient an element that has a nucleus that emits positrons. And so basically that will then go to the tissue it's aimed at. It could be the brain, in this case it's the brain. And when those positrons which are emitted meet electrons in the atoms in your body, they annihilate into oppositely directed high energy photons known as gamma rays. And those gamma rays can be detected. And from those gamma rays, it's possible to deduce a picture of the tissue, whether it's the brain or whatever. So antimatter has a really everyday important use. Now, when matter and antimatter annihilate, 100% of the mass energy of the two particles is converted into other forms of energy, eventually heat. In something like a hydrogen bomb, 1% of the mass energy of the material is converted into the heat of the fireball. So pound for pound, antimatter is a source of energy which is 100 times more concentrated than nuclear power. And that is, of course, why the Starship Enterprise was powered by antimatter. My final magician is this man. His name's Karl Schwarzschild. He was a German astronomer. He was director of the Berlin Observatory at the outbreak of the First World War. He immediately volunteered to join the German army. And this was perhaps a surprise to everyone because he was 40 years old. But it turned out he was Jewish. He wasn't a practicing Jew, but anti-Semitism was on the rise in Germany. And he wanted to show that as a Jew, he was a patriotic German. Anyway, he worked with an artillery battery in France, calculating shell trajectories. He then worked with a weather station in Belgium. But in the winter of 1916, he developed blisters inside his mouth. He didn't really think much more of it, but these blisters spread until they covered his whole body, until he was covered in suppurating, bleeding blisters. Well, he ended up in a field hospital on the Eastern Front, on the Russian front. And it took a while before the doctors figured out what was wrong with him. And they diagnosed something called pemphigus vulgaris, which is quite a rare disease. It's an autoimmune disease in which the body's immune system attacks the skin. So once Schwarzschild knew this, he knew that his life was in peril because your skin is your biggest organ. It's through your skin that you lose excess heat from your body. So if you can't remove that heat, you could overheat and die. And of course, your skin is a barrier against infection, against microorganisms. So if that's compromised, you can potentially die of an infection. Anyway, lying in bed, he tried to distract himself from all these thoughts by doing physics. And when he'd been in Berlin, he'd known of Albert Einstein. He was not a colleague of Einstein's, but Einstein was also in Berlin. He knew Einstein to say hello to, although he'd never had a conversation with him. And he knew that Einstein had been devising a new theory of gravity. And he discovered that Einstein had presented his new theory in 4 lectures at the Prussian Academy of Science in Berlin in November 1916. And within weeks, he obtained papers, which he devoured. Now, Einstein, this is Einstein in his rock and roll days. How is his theory different from Newton's? Well, Newton basically imagined a force of gravity between the sun and the earth, rather like an invisible tether. And that tether kept the earth constrained to orbit around the sun forever. But Einstein realized that that picture was false. There was no force of gravity between the sun and the earth. What a mass like the sun does is it warps or distorts the space-time around it. Now, we can't see that because space-time is a four-dimensional thing. That's why it took the genius of Einstein to realize. So it creates a valley in the space-time around it, and the Earth moves around the upper slopes of that valley because that's all it can do. It moves rather like a roulette ball in a roulette wheel. So the problem with this theory was that it was very complex. What you needed to do was to work out the curvature of space for any given mass. But it turned out that whereas Newton had just one formula to describe gravity, Einstein replaced it by 10. So working out that curvature of what we call finding a solution of Einstein's equations was horrendously difficult. In fact, Einstein had to approximate the curvature of space, the valley of space-time around the sun. And with that approximation, he was still able to predict the motion of Mercury and explain the anomaly in its motion. But Schwarzschild, lying in his hospital bed, was sure he could do better. And incredibly, he found an exact solution, the exact description of the valley of space-time around the sun. And with that exact description, he was able to predict the motion of Mercury. And he wrote it up as a paper, posted it to Berlin. And when Einstein opened the letter, he was amazed. First of all, he got a letter from the Eastern Front that he didn't expect. And secondly, when he looked at the letter, he realized that somebody had done something he thought was impossible and found a solution of his equations. Well, he wrote back and said he was incredibly impressed. He then presented this result on behalf of Schwarzschild the following week at the Prussian Academy. But Schwarzschild had not finished. He'd worked out the curvature of space-time outside a spherical mass like the sun. For his next trick, he tried to work out what it would be like inside. And he discovered something amazing. If the mass was squeezed into a smaller and smaller volume, the valley would become steeper and steeper. And eventually, when the mass was concentrated in an incredibly small volume, the valley would turn into a bottomless pit from which nothing, not even light, would escape. Now, he had no word for this object, but of course, there's hardly anyone on Earth today that doesn't know the name of this object. It's a black hole. Anyway, he wrote up his paper, sent it to Einstein. Einstein duly presented it at the Prussian Academy. But Einstein never believed in black holes. He was sure that they were some kind of monstrosity and that some other force of nature would intervene to prevent a mass collapsing or shrinking or being compressed small enough to curve the space-time, wrap the space-time around it into a black hole. So poor old Schwarzschild, he was moved to a hospital in May 1916 in Berlin, where he died. And now we fast forward half a century to this place. This is Herstmonceux Castle in East Sussex. It's a 15th century castle surrounded by a moat, and it was the location of the Royal Greenwich Observatory. And these two people are important. On the left is the astronomer Louise Webster, who was about 30, and on the right, Paul Murdin, who was also about 30, and they were office mates at Herstmonceux. Now, Murdin had been working for about 7 years in America, on the east coast of America, and he'd just come back to England. This was in 1971. And the big problem in astronomy is, how do you find something interesting? I mean, there's 2 trillion galaxies, each of which contains 100 billion stars or so. So finding an interesting star is like finding an interesting sand grain on a beach. So when he'd been in America, Murdin and his fellow students, his fellow graduate students, had often over coffee discussed how you would find an interesting object. And Murdin had come to the conclusion that if an object emitted X-rays, it would be interesting. Now, X-rays are a type of high energy light. Obviously, we use them for medical X-rays. And they are produced by matter which is heated to hundreds of thousands or millions of degrees. So Murdin thought, well, God, any object that's millions of degrees is bound to be interesting. Now, it turns out that X-rays are cut out or absorbed by the Earth's atmosphere, which is good news for us. But in the early 1960s, Riccardo Giacconi, an Italian-American astronomer, had begun launching sounding rockets up into the atmosphere. These were little rockets which just went up, reached a high point, and then fell back down to the Earth. And they carried very crude X-ray telescopes. And with these telescopes, he discovered that there were X-ray sources in the sky. But the telescopes were very crude, they had very blurry vision, and so he could only determine which constellation the X-ray sources were in. Now, one of those sources was called Cygnus X1. It was in the constellation of Cygnus the Swan. So the next development in X-ray astronomy was the launch in 1970 by NASA of Uhuru. Here it is. This was the first X-ray telescope. And it could not only observe the X-ray sky for extended periods because it was above the atmosphere, it had sharper vision than Giacconi's telescopes. So Murdin obtained, while he was at Hurst-Monsoon, he just arrived at Hurst-Monsoon, he obtained a catalogue of the objects it had observed. And he looked for Cygnus X1, and he found that the box showing the possible location of Cygnus X1 had shrunk. It was no longer the whole of the constellation of Cygnus, it was shrunk down smaller than that. And he looked for an interesting object, and there was an interesting object in the box. It was a blue supergiant star, a star which was probably in the range 25 to 50 times the mass of the sun, and it was pumping out hundreds of thousands of times as much energy as the sun. So that was an unusual object. It couldn't be the source of the X-rays because it wasn't hot enough, but maybe it had a companion onto which material was being sucked that was the source. It turned out that Louise Webster, his office mate, was measuring the speeds of stars in our galaxy. It was a project that she was involved with the director of the observatory, Richard Woolley. So how do you measure the speed of a star? You use the Doppler effect, which we're all familiar with. As a police car comes towards us, its siren gets more shrill, higher pitch, and as it moves away from us, it goes to lower pitch. Well, light has a pitch as well. It's called its frequency. High pitch light is more blue, low pitch light is more red. So you can actually determine whether a star is moving towards us or away from us if its light is red or blue shifted. So Murdin gave the coordinates of this blue star to Louise Webster, and she went away and observed it with a lot of other stars from the 100-inch telescope, the Isaac Newton telescope at Hurst-Monsoon, which was one of the biggest telescopes in the world, but built in probably the worst location. It was nearly always cloudy. And eventually it would be moved to the Canary Islands at a greater cost than the cost to initially build it. Anyway, she made the observations, and it turned out that the blue star was orbiting something. It was periodic, its velocity was periodically changing. It was orbiting something invisible. So the question was, what was it orbiting? So one day, Louise Webster and Paul Murdin sat down at their desk. They were in an octagonal turret room of Hurst-Monsoon Castle, and their window looked out across the moat to fields where there were geese grazing. It was an idyllic place. Anyway, they sat down and they were able to determine, using Newton's law of gravity, what the mass of the invisible object that the blue supergiant was orbiting was. They couldn't be absolutely sure, but they could tell that it was at least 4 times the mass of the sun, possibly as much as 6 times the mass of the sun. So they went through the objects that it could possibly be. I mean, one was a white dwarf star. This was the end point of the evolution of an ordinary star like the sun. The sun will become a white dwarf one day. A white dwarf is incredibly faint. It's about the size of the Earth, but it packs the mass of a complete sun. But it turned out that there was a limit on the mass of a white dwarf. It couldn't be more than about 1.5 times the mass of the sun. But this object had to be at least 4 times the mass of the sun. So that was ruled out. The next possibility was a neutron star. Now, these had been discovered by a graduate student at Cambridge called Jocelyn Bell 4 years earlier in the guise of what we call pulsars. And these objects were about the size of Mount Everest, but again packed the mass of a complete sun, and they were very faint. But again, there was a mass limit on how big they could be. They couldn't be more than about twice the mass of the sun. So that left just one possibility. And Murdin and Webster exchanged glances, and they realized that what they'd actually discovered was the object which had been predicted by a man dying of an agonizing skin disease 50 years earlier, a black hole. So this is what Cygnus X1, we believe, looks like. The blue supergiant star has material dragged off it by the gravity of this black hole, and it swirls down through what we call an accretion disk onto the black hole. And as the material swirls around, friction, internal friction, heats it to millions of degrees, and that is the source of the X-rays. Where you would think, having discovered a black hole, something that Einstein himself never believed in, you would think that there would be no problem in publishing that result. However, Richard Woolley, who was the director of the Royal Greenwich Observatory, was a very cautious man. The problem was that the Greenwich Observatory had been run by the Navy until a few years before, and they were very cautious. So Woolley did not want the observatory to get egg on its face. He did not want them to predict the existence of something which turned out to be a fiction. But finally, they did manage to persuade him, and Murdin rushed up to London with his paper to the British science journal Nature. He was worried that someone else might pip him to the post, someone else might make this discovery. And it was announced in 1971 that black holes had been discovered. Now, it turned out that Murdin didn't even have a permanent job, and that's why he wanted to discover something important, and that's why he wanted to make his name. And he got a permanent job, and he got to buy a bigger house. So he was the first person in history to have his mortgage paid by a black hole. And he celebrated with his wife and his 2 boys, who were aged 2 and 5, with Knickerbocker glories in a beachfront cafe in Hastings. So, I mean, what an amazing contrast that the man who'd actually discovered these black holes was dying of a agonizing skin disease in a World War I field hospital, and the man who found them celebrated by buying Knickerbocker glories for his 2 little boys. And presumably they hoped that their dad would discover more black holes. Now, it turns out that black holes are not anomalous at all. We thought they were kind of monstrosities. They have infinitely strong gravity. They're nightmare objects. We thought that they were, if they existed, they would probably be very rare. But actually, we discover that there's a supermassive black hole in the heart of every galaxy, including our own Milky Way. We've got a Tiddler, which is about 4.3 million times the mass of the sun. But in some of these objects known as quasars, some of these galaxies which are known as quasars, the black holes can be up to 50 billion times the mass of the sun. And they project from their poles these amazing jets of material which extend often over millions of light years and affect their surrounding galaxies. Nobody has the slightest idea why there's a supermassive black hole in the heart of every galaxy. And nobody knows exactly how they formed. Nobody knows whether they formed first in the universe and became the seeds around which galaxies of stars coalesced, or whether the galaxies of stars formed first and the black holes then collapsed in their cores. These are all great cosmological mysteries. But in April 2019, something amazing happened. We got our first ever image of a black hole. Now, the image was obtained by the Event Horizon Telescope, which was an array of radio dishes spread across the globe. And the idea is that each of these dishes observes an object in the sky, the same object at the same time, and the signals are recorded on magnetic tapes, which are flown together and are combined in a supercomputer or a correlator to create an image, the image that we would have obtained if we had a telescope the size of the Earth. The importance of that is that the bigger your telescope, the finer the detail that you can actually see. Okay, so in order to see something as small as a black hole in the heart of a galaxy, you need this giant array of telescopes. And in April, this picture was presented by the Event Horizon Telescope team. And it is the first ever image of a black hole. It's a black hole, a supermassive black hole in the heart of the galaxy M87, which is a nearby galaxy. And if this is, first of all, I should tell you that the black hole is at the center of this donut. It's been backlit by incredibly hot material swirling into the black hole. So that's what that donut is. And you can see how big this black hole is. Pluto was considered to be the outermost planet until it was demoted to a dwarf planet, but effectively gives us the outer edge of the solar system. So this object is much bigger than the solar system. And a lot of people were underwhelmed by this image, but I think it's probably one of the most important images in the history of science. Probably it ranks with the Apollo image of the Earth rising above the moon and the double staircase, the double spiral staircase of DNA. Because what we're actually seeing here is the edge of the black hole. So look at the black void at the center. Matter is pouring over into that void across what we call an event horizon, a point of no return for light and matter. And it's like water going over a waterfall. The light and the matter goes across this horizon and is never seen again in our universe. And inside a black hole, space and time actually come to an end. So it's very easy to do us humans down, to say we've polluted the planet, we've created greenhouse warming, we've overcrowded it, we've done all these kind of things. But sometimes I think we need to pat ourselves on the back. We are a jumped up ape that evolved on an African plain 3 million years ago with a brain, a 3-pound brain made mostly of jelly and water. But we have seen to the very edge of space-time. Now we come to, why does this magic work? Why was it possible with a mathematical formula written down on a piece of paper to predict the existence of a new planet, Neptune, to predict the existence of radio waves, to predict the existence of antimatter, to predict the existence of black holes? Why does the universe have a mathematical twin that mimics it in every way? Or in the words of the Austrian physicist Eugene Wigner, why is mathematics unreasonably effective in the natural sciences? Well, there are lots and lots of suggestions, so I'm just going to mention two. And the first comes from this man, Stephen Wolfram. Wolfram is British. He was born in London. He was a bit of an infant prodigy. He was publishing papers in the physics journals when he was a teenager. And he invented a computer language called Mathematica. And he's now a billionaire. Wolfram thinks that the universe is not mathematical. He thinks it's just an illusion. And he gives this analogy. He imagines a drunk looking for their car keys at night, their dropped car keys. Where do they look? They look underneath a street lamp. They look there not because it's the best place to look, but because it's the only place they can look. And what Wolfram thinks is that the universe is not mathematical, but we only see the bits which we can actually explain mathematically. It's rather like the streetlight again, illuminating what it can illuminate. Mathematics illuminates what mathematics can illuminate. So the question is, if the universe is not mathematical, how do you describe it? Well, obviously, there is order in the universe. It isn't completely chaotic. So if you don't use mathematical formulae, mathematical equations, what can you use? Well, Wolfram got a hint in the early 1980s when he bought one of the first personal computers, an IBM PC. And he started playing with it and looking at simple computer programs, they're called cellular automata, to see what their output was. So he would basically get the output from his program and feed it back in as the input and keep doing that, rather like a snake eating its own tail. And in most instances, he found that the output was extremely boring. But very occasionally, he found that the output was incredibly complex. It never repeated. It was infinitely novel. And this was a really striking observation because normally simple computer programs have simple outputs and complicated computer programs have complicated outputs. What he had found was simple computer programs that had very complex outputs. And he began to wonder, is this what nature is doing? Is it running computer programs? Is it the secret of how it can create a rose or a newborn baby or a galaxy? So what Wolfram thinks is the universe is running a computer program. It's been running it for 13.82 billion years. And the output of that computer program, really you can only find by running the computer program for 13.82 billion years. However, Wolfram thinks that within this giant calculation which is going on, and we're part of it, you're part of the calculation, are islands where you do not have to run the computer program to get the output. You can actually predict the output ahead of time. And these islands are mathematical physics. But Wolfram's ideas are controversial, and most physicists still believe that what the universe is doing is mathematical. So here's another explanation of why the magic of science works, the central magic of science works. This man is called Max Tegmark. He's a Swedish-American physicist, and his explanation of the magic of science has to do with multiple universes. Now, it appears that nature has been banging us over the head and telling us that this universe is not the only universe. So this is the idea of the multiverse. And the multiverse idea comes in many versions. So for instance, there's a multiverse in which the individual universes have different laws of physics. There's a multiverse in which each universe has different constants. So for instance, different strengths of gravity, different masses of the electron. There are multiverses with different numbers of dimensions. Nobody knows how all these multiverse ideas mesh together, but that's what you expect for an emerging idea. Well, Tegmark has come up with this idea of the ultimate multiverse, what he calls the ultimate ensemble. And what he says is there are an infinity of universes, and in each there is a piece of mathematics. So in some of these universes, there is, say, the mathematics of geometry or flat paper geometry. In other universes, there may be Boolean algebra or topology, but in all of these universes, the mathematics is not complex enough to create anything interesting. But in some of the universes, a handful of the universes, in this infinity of universes, Tegmark says that there is mathematics which is complex enough to create stars and galaxies and planets and intelligent life. These universes contain a piece of mathematics that we have dubbed the theory of everything. And of course, we find ourselves in such a universe because how could we find ourselves anywhere else? So really what Tegmark is saying is that the question of why the magic of science works, why mathematics is so effective in the natural sciences, the answer is incredibly simple. The answer is that it's effective because mathematics is physics. Now, I really like the idea of the multiverse because it gives me a good way to finish this talk. There is another multiverse in which all possible histories are played out. I apologize for the sexist picture, but that's the only one that I could actually find that illustrates it. In this multiverse, all possible histories are played out. So there's a universe, for instance, where you didn't tune into this YouTube video today, but decided to do something more interesting. There's a universe where Donald Trump did not become president of the United States and Boris Johnson didn't become Prime Minister of Britain. There is a universe where the dinosaurs were not wiped out by an asteroid 66 million years ago, but went on to develop intelligence and build motor cars. Why do I like this multiverse? Well, even if this is the most tedious, most boring, most dull talk you've ever listened to, I can console myself that in an infinite number of other universes, you thought this was the best talk you'd ever heard of and recommended my book to all of your friends. Thank you.